What if the next giant leap for AI isn't about writing perfect code, but about embracing chaos? Today, we're diving into a totally new kind of artificial intelligence that computes using the messy, unpredictable laws of physics. We're talking about a hardware revolution that promises insane efficiency, but, and this is a big but, it comes with a ghost in the machine.
Okay, so here's the game plan. First, we're going to look at this huge wall that modern AI is slamming into. Then, we'll dive into this wild solution, analog computing, and unpack its hidden flaws. And finally, we'll see how the entire industry is trying to create a universal language, basically a rulebook, that might just be the key to us ever trusting these new forms of AI.
All right, first up, AI's insatiable memory hunger. So, you might be asking, why do we even need this crazy new hardware in the first place? Well, to get that, you've got to understand the massive bottleneck that's holding back AI right now.
So here's the deal. Modern AI is about to hit a wall, hard. As these models get bigger and smarter, our computers, they're just starting to choke. And the crazy part is, it's not the thinking part that's the problem. The processors are lightning fast. No, the problem is the commute. AI wastes most of its time and energy just creating this massive digital traffic jam, shuttling data between the processor and memory.
And that commute has a name, the memory wall. Think about it. It's this bottleneck caused by the simple fact that the processor and the memory are physically separate. It wastes an absolutely massive amount of energy and time, just shuffling data back and forth, sometimes only a few millimeters. The inefficiency is so extreme, it's forcing the entire industry to reinvent the computer from the ground up.
So that brings us to our next chapter, A New Hope, Analog AI. If the problem is moving data, what's the solution? Well, it's a pretty radical one. What if, instead of moving all that data to the processor, we could just make the memory itself do the thinking?
And that idea is called analog in-memory computing, or AMC. It's a total game changer. The core idea is to literally use the laws of physics, like Ohm's law and Kirchhoff's law, to do math. You represent data as a physical thing, like how easily electricity can flow through a material. And when you do that, you can perform these gigantic calculations, like a whole matrix multiplication, basically, instantly, in a single step. We're talking up to 100 times more energy efficient. It doesn't just chip away at the memory wall, it completely demolishes it.
Now, as you can imagine, a promise like that has kicked off an absolute wild west of innovation. Seriously, labs and companies all over the world are in this frantic race to build the perfect analog memory device. It's just this explosion of different materials, different physics, each one a brilliant but totally competing idea, all fighting to become the foundation for the future of AI.
And this race has given us some really amazing contenders. It's kind of like a tale of three different technologies. You've got FEFET, which is like the talented rookie. It uses these tiny electric fields to flip microscopic compass needles, super fast. Then there's Flash, which is like the reliable veteran. It's the same tech in our phones, storing electrons with really high precision. And then you have phase change memory, or PCM. That's the mature specialist. It actually stores data by zapping a material to switch it between being an orderly crystal and a messy, glass-like state. Each one is totally brilliant in its own way, but, and here's the catch, every single one of them has a hidden and potentially fatal flaw.
And that brings us right to the heart of the problem. We're calling this section the ghosts in the machine. Because for all their incredible promise, all these analog chips, they share a common set of spooky problems. Which leads to the million-dollar question, right? What if these revolutionary chips simply can't be trusted? I mean, what good is a brain that's 100 times more efficient if you can't actually rely on its answers? That is the fundamental challenge of analog AI.
Okay, so the first ghost is just pure randomness. The fancy word for it is stochasticity. See, down at the atomic level, the physics is just messy. It's probabilistic. When one of those FET devices switches, it's not a nice, clean flip. Oh no! It's this chaotic swirl of tiny crystal domains growing and merging, and it's never perfect. What that means is every single calculation has a little bit of noise baked right into it, and that's a huge problem when you need answers you can count on.
The second ghost? Honestly, it's even spookier. The chips slowly forget. We're talking about a fading memory. The physical states that store the information, they just aren't perfectly stable. In phase change memory, that glassy structure slowly relaxes. In the FEFETs, there's an internal electric field that's always trying to push the little domains back. This is called conductance drift, and it means that a value you store today will not be the same value a month from now. It's like a photograph fading in the sun.
The memory literally just degrades over time.
And this is where it gets really interesting. In this whole wild west of competing technologies, there's a surprising point of agreement. It doesn't matter what material you're using, ferroelectrics, phase change glass, you name it, every single developer is fighting the exact same 5 battles. You've got the randomness, the fading memory, the fact that it's easier to strengthen a connection than to weaken it. This shared struggle, this common enemy, has created this totally unexpected common ground for everyone to work together.
Okay, so with everyone basically facing the same 5-headed monster, the industry is actually coming together to write a common rulebook, a universal language for this new type of hardware, all designed to try and tame this chaos. This is the Signal Standards Framework.
And this quote really says it all. This effort, which is being laid out in the new Signal Standards Framework, basically admits that you can't just slap the old digital rules onto this new analog world. It just doesn't work. It requires a complete paradigm shift, forcing us to rethink something as basic as what even is a value inside a computer.
And that is a total mind bender. Think about it. In your laptop right now, a value is absolute. The number 5 is always exactly 5. Perfect. Deterministic. But in the analog world, that's just impossible. So the new standard, it embraces the uncertainty. It says a value isn't a single perfect number. Instead, it's a target with an acceptable margin of error around it. It's a statistical distribution. We are fundamentally redefining what information is.
The official name for this is statistical state specification, and it's the foundation for this whole new system. Instead of trying to program a chip to be exactly a certain value, you program it to have a target value, and you accept that the actual result is going to fall somewhere within a predictable range, or variance. It's a language built entirely on probability, not on certainty.
So, once you have that foundation, you can start building a language of trust. The framework proposes 3 key steps. First, you standardize how values are represented, so everyone's using the same ruler. Second, you create different precision tiers, so you might have a super accurate training grade for when you're teaching the AI and a more relaxed inference grade for when it's just doing its job. But maybe the most clever idea is something called differential encoding. To store just one value, you actually use 2 memory cells. Now remember how they drift over time? Well, they tend to drift together. This means the difference between them, which is the actual value you stored, stays remarkably stable. It's this brilliant little trick using the flaws of physics to cancel themselves out. All right, so let's bring this all home. From chaos to certified AI, why does any of this highly technical stuff actually matter to you and me? Well, it turns out it has huge implications for our safety and our everyday lives.
Yeah, this isn't just about faster chips or some academic debate. Let's get real. If an analog AI chip is running the safety systems in your self-driving car, that conductance drift we talked about, that's not just some quirky bug. That's the AI literally slowly forgetting what a stop sign looks like over the course of a year. So we absolutely have to be able to prove, mathematically and legally, that these systems are reliable.
And that is exactly where these standards become essential. They create a clear, auditable path for these new chips to actually get certified under super strict regulations, like the EU AI Act for high-risk systems or ISO 26262 for the automotive industry. By creating a shared definition of what reliable enough actually means, we can finally build systems that we can certify, and more importantly, trust. And it even lets us turn a weakness into a strength. That inherent randomness, you can use it to create unique, unclonable security keys for the hardware itself. Pretty cool.
And look, this isn't just wishful thinking. There's a clear roadmap in place. Over the next couple of years, the goal is to establish the basic language for measuring these devices. From there, the industry will build common software tools, get aligned with all those safety regulations, and ultimately create a whole thriving ecosystem, all built on this new language of trust.
So that leaves us with one final big question. The entire journey of analog AI is about going from this brilliant but chaotic mess to something predictable and reliable. By teaching these machines to speak a common language, one that's built on managing imperfection instead of demanding perfection, are we finally getting ready to trust them with our future?